Hello. So today I will start with introduce myself first. So my name is Muhammad Afiq bin Muhammad Saleh. Message number CE220101. So today I will present electronic circuit analysis and design about four order bandpass filter. So I will go to introduction first. The introduction is creating and analyzing circuit for electronic device is essential in electronic circuit design. Operational amplifier are critical for amplifying and filtering signal. Active filter use op-amp to filter out unweighted frequency with bandpass filter of other 1 to 4 allowing specific frequency range to pass through. For order bandpass filter use op-amp, resistor, and capacitor to maintain desired frequency while attenuating others. Designing this filter requires a deep understanding of circuit analysis and op-amp behavior. Engineer use this filter for various applications like signal and audio processing. There's electronic circuit design, especially involving op-amp and active filter, is vital for enhancing the functionality and quality of electronic system and device. And then I go to objectives. For the objectives, to design the four order bandpass filter with the specific frequency. Low cutoff, which is FL equal to 1.5 kHz, and high cutoff, which is FH equal to 50 kHz. And second, to construct the filter using the suitable op-amp and resistor. Third, to test the frequency response of the filter. And last objective, to study the difference between the simulation result and the actual result of the filter. So I will go to the next.
Calculation of low-pass filter and high-pass filter. Based on the theory of the Butterworth filter, we can calculate the resistors RA and RF for active low-pass filter. Assume RA1, RA2, R1, R2, R3, R4 equals to 10 kilo ohm, RF1 is 12.35 kilo ohm, and RF2 is 1.52 kilo ohm. And then calculation of the capacitors of active low-pass filter is 1.06 nanofarad. For the calculation of resistors RA and RF of the active high-pass filter, we assume RA3, RA4, R5, R6, R7, R8 equals to 15 kilo ohm, and RF3 is 18.5 kilo ohm, RF4 is 2.28 kilo ohm. And then calculation of the capacitors of the active high-pass filter is 7.07 nanofarad. Calculation of gain and non-inverting amplifier for second-order circuits cascade in succession. The total gain or AT was computed by using this formula, and we get the total, which is 6163. And then using this formula, we get 11.31 is the gain of non-inverting amplifier. We can assume RA5 is 15 kilo ohm. RF5 is 154.65 kilo ohm. For the simulation, we do the simulation in multisim. For low cutoff frequency, which is here 1.5 kilohertz, the mid gain is 34.45. And for the high cutoff frequency, 15 kilohertz, which is here, the mid gain is 34.45.
Hi guys, I am Valentine Teodigno. My metric number is CE210010. So, we are from group 6 and today I'll present about our experimental result for this project. Okay, so now we will start with looking at this waveform, right? So the yellow one is channel 1, which is the input. Okay, you can see that over here. The voltage peak to peak is 10 volt, and then the frequency is around 100 hertz. So the second one is the output, which is channel 2 also. The peak to peak value is 212 millivolt, and then the frequency is around 50 hertz. Okay, let's move to the next slide. Okay, now I will show you that this is the result table of our experiment. So we'll have four elements, which is the first one is frequency, and then the second one is input voltage, the third one is output voltage, and then the gain is the last one. And in gain 2, we also divide to two sections, which is the uniless and then with the dB. So we setting the function generator, right? We set starting from 100 hertz, as you can see that over here. So when we set to 100, right, and then the input voltage will be 10 volt, and then the output voltage will become 0.012. So that's all we got from the simulation physically. So how to get the gain? To get the gain, right? If you want to get the uniless, right? So the formula will be AV equal to voltage output divided by voltage input. So after we do the formula, right, we'll get the value is around 0.0012. And then to get the dV gain, the formula of dV gain is 20 log 10 and then gain. So after that, you'll get the value which is the negative one, negative 58.42. Okay, after that, right, we'll continue increasing the frequency of from the function generator. You can see that from the table. We're increasing 100 to 200 and then 200 to 300. We'll keep continuing this process until we get until 30 kilohertz for more accuracy result. So this is the continuous result from based on the previous table. Because it is way too long, so I have to cut it right until 1000, 17,000 kilohertz. Okay, now let's move to the next slide again. Okay, now we'll discuss about the comparison of result. So for the result part, we'll have three type of result, which is the first one is theoretical result, simulation result, and then the experimental result. So you will have five element also. So the first one is mid gain, and then gain to get a cutoff frequency, low cutoff frequency, high cutoff frequency, and bandwidth. So for the theoretical result, right, the mid gain value is 37.5, and then the gain to get the cutoff frequency is 34.5, which is already minus by 3. So for the low cut-off frequency, it is in theoretical way, right? It is 1.5K, and then the high cut-off is 15K. So how to get the bandwidth? The formula of bandwidth is high cut-off minus low cut-off, and then we'll get 13.5K. So for the simulation result, right? We get the simulation result from the application multi-sim. So it is 100% corrected to it is 100% same with the theoretical result because we are using the theoretical result to run the simulation. Okay, so the last one is experiment result. So the mid gain is 34.57, and then the gain to get the cutoff frequency is 31.57, which is already minus by 3 dB. Okay, so for the low cutoff frequency is 1.55K also, and then the high cutoff frequency is 15.3K. So for the bandwidth of this experiment result, right, is around 13.75K. Okay, so now we'll move to the next part then. And now I will present about the discussion. So let's start with the overview of the key parameter. The first, so it will be mid gain, cutoff frequency for FL and F hash, the center frequency, and the bandwidth. So first, we'll look at the mid gain, which is the crucial for understanding the filter operational range. The theoretical and the simulation value it show that a minimal difference of just 0.004%. So this high level of agreement indicate that both theoretical calculation, right, and then the simulation are reliable for predicting the mid-gain accuracy. So the next one, let's examine the cutoff frequency, the FL and then the F hash, which define the passband limit of the filter. So there's a perfect match for FL between theoretical and simulation result. And then for the F hash, right, there's a slight 0.14 discrepancy, which is still acceptable by the engineering tolerance. Okay, so even though the specific percentage error for the center frequency FO and then the bandwidth are not so detailed, but this parameter also can be able to assessing the filter performance. Okay, so that's from the discussion, right? If we want to improve our accuracy in fuser design, we are recommended to use the following step, which is ensure the precise component value in simulation to match the theoretical calculation. So in our project, right, uh, the value of the component is slightly different from the simulation because it is quite hard to get that value because we have the limited component. Okay, so I think this is all for me. Thank you.
So the conclusion is we construct a four-order active bandpass filter using 5 op-amp, 2 for low pass, 2 for high pass, and 1 non-inverting for stability. Rigorous lab testing highlighted the importance of this resistor and capacitor values for accurate frequency and gain. With our prototype validating active filtering and frequency response theory, although experimental results show higher percentage error than simulation. Using multi-sim and center frequencies, generally confirming our theoretical prediction. This project effectively demonstrates the practical application of active bandpass filter principle. So I think that's all from our group. I hope you enjoy this video. So thank you.